that had to go also. So
Take 3.
take 3. So counting. Factorials, permutations, combinations. You've seen this before in some capacity or another. But the thing is, it kind of got, it used to play a prominent role in Math 2, which was the equivalent of geometry, right? So like freshman, sophomore math. It used to be a big part of that course. And then it kind of disappeared. And then it came back sometimes in middle school, sometimes in sort of like disjointed topics here and there. But it never got its like full, just due, I guess. So a factorial is that exclamation point. That you probably should be pretty familiar with. But the permutations and combinations maybe a little less so. Factorial is just talking about a full arrangement of n items, all right? So I'll just keep it simple. For the first case, we're talking about a group of 3 people being arranged in a line. How many possible arrangements are there, right? So, in the form of a tree diagram, you could do any of the 3 people could occupy the first position in line, right? Then once the first person is placed, right, 2 individuals aren't going to occupy the same place at the same time. What is that called? It's a science term.
Time travel?
Yeah, but there's a name for it. When an object can't occupy the same position at the same time. Uncertainty principle, yeah. So A is situated. So A can't be in the second position on line. And so when A's in position, then it can only be B's in position, then A or C can only occupy the second position. Same idea for C being in the first position, then only A or B in the second position. Now, you can already see how this could get out of hand if you have 20 people that you need to arrange in a line, right? If A and B occupy the first position, then it must be person C in the last position. So process of elimination tells us that AC then B, BA then C, BC then A, CA then B, and CB followed by A. So we're not assigning probabilities here because we're only accounting for different possible outcomes. I don't know what the probability is of any person being in a particular position in line. All right. So now throw a little context into this, and I say, you got 3 people, and they're told to get in line as fast as they can. Person A is twice as fast as person B, and person C is 1/3 as fast as the person B. Now you're talking some probabilities that can alter the overall chances of a particular arrangement happening. All right, so you can see how this gets jazzed up pretty easily. All right, but as it stands right now, if everything's equal, then this would be the distribution. All right, so we'd have a total of 6 possible outcomes. All right, for the first position, we add any of 3 people. For the second position, we add any of 2 remaining people. And for the last position, we had whoever was left over. So multiply those values. 3 times 2 times 1 is going to give you a 6. All right. That 3 times 2 times 1, shorthand notation could be represented as 3 factorial. All right. So 3 factorial is really just saying for you to take a number, multiply it by a consecutively lower and lower number until you get down to 1. All right. Now, there are some weird properties that emerge from this that we'll talk about later. And that is, like, for example, 0 factorial is equal to 1. Conceptually and also mathematically, that does work out. Conceptually, it should make sense. Like, how many different ways can you arrange nothing? Well, here's your nothing, one way. All right, but mathematically, the idea of multiplying involving the number 0 just feels wrong to end up with anything other than 0. But I'll show you the proof later on that'll help you understand that. So a couple of cases here, well, one case numerically and one case in terms of a general rule. This plays out kind of nicely. Now, for you BC students, yeah, have you gotten to Taylor series and things like that yet? No?
We do infinite series.
You've done? Okay. So, yeah, once you get to infinite series and stuff like that, this rule is going to play a pretty big part. You know, so you're gonna kind of go back and tackle this again. But the ideas of permutations, combinations, and factorials, they play a pretty big role in Taylor, Maclaurin series, and all that good stuff. All right, so more on that later, I guess. Number 2, now we're going to kind of restrict things a little bit. A line consisting of 2 people must be arranged from a group of 3 people. How many possible arrangements are there? Well, we already did it up here. I'm not going to reinvent the wheel. It's only really talking about this restriction here, right? It's the same number of people to start, but I only need 2 positions. A little bit bigger, I guess. So in this case, all it's asking me to do is take the 3, multiply it by the 2, and I'm going to get a result of 6 also. So it's kind of weird to think about the fact that there's a restriction and yet there's no restriction, right? Because in this case here, when I create a line consisting of 2 people, I am really accounting for all 3 people. It just doesn't seem that way, right? Because the third person is just told to go home, right? But there's still something going on with that third person, all right? So I got A, B, C, get out of here. A, C, B, get out of here, and so on. But you still have to do something with that third individual to account for the fact that they're part of the original group, all right? I only need 2 of them, but that automatically puts the leftovers in another group. Now, if I had, for example, like 20 people, and I wanted to create groups of 2 or arrangements of 2, then it would be 20 20 times 19 times still 1, because all the leftovers would be categorized in one irrelevant group. All right, that's not good for their emotional well-being, I guess, but that's really what it amounts to. We got any of the 20 possible people in this group, in this position, any of the remaining 19 in this possible position, the remaining 18 can go bugger off. I don't know if that's a bad word. I like saying it though. Like it's like one of those British words that when you say it, it could be like completely benign and totally fine, but it could be like the most morally reprehensible and profane thing that I could possibly say. I hope it's not that. Like, I only learned recently, but you can look it up. It's, I wouldn't say, I said horribly, but not horribly. It's not like you're going to blush, but you're going to be like, whoa, that's what it means?
Huh.
That's pretty
I
crazy.
thought it was just like a little mix-up.
Yeah, that's what it means in commonplace English, but it's an acronym for something that has a bad word in it. Yeah. So, fun fact of the day. FFOTD. So, we have this now. I can look at this as a permutation and call it 3p2, where 3 represents the number of individuals and the 2 represents the number of positions. All right, so it's shorthand notation that allows me to take something like, if I had 20 people and I wanted 5-person arrangements, 20p5 would get the job done. But then what's the benefit of doing that? Well, math probability in your calculator, you have a nice menu that has factorials, permutations, and combinations. So we'll pick up with this on Monday, and then we'll continue with projects and stuff like that. So a lot of good stuff. Idea that a permutation is a restriction on a factorial. All right. So instead of out of the 3 people lining them all up, I'm only lining 2 out of the 3 people. So the 3 would represent the number of individuals, and the 2 would represent the number of positions available. And so in this case, what I'd be looking at is the 2 giving me the number of blanks, if I were doing this by hand, that I would draw out, and 3 representing my start. And then I would just keep declining by consecutive values until I fill in all the gaps, all the spaces. All right, so I would end up with a product of 6. All right, and I mentioned last time that it's an implied factorial equivalent relation because you're dealing with 2 people being arranged, but naturally that third person is an arrangement in and of themselves. All right, they're just not going to be on the line. They're the go home arrangement. All right, get out of here arrangement. All right, so there's still 6 ways that this would play out. That explains why it's consistent with 3 factorial. Right? There also is a general rule, and we could do this in a calculator, so we don't really need the general rule, but it's kind of interesting. So, and also, you know, AP. You never know how they're going to ask something. So n factorial over n minus r factorial. So if I want 3p2, I'm looking at 3 factorial over 3 minus 2 factorial. And so that ultimately just ends up being 3 factorial because 3 minus 2 is 1, 1 factorial is 1, so 3 factorial. So we have a little mathematical justification for why 3p2, you know, conceptually we have the justification, but now we also have a mathematical justification that 3p2 and 3 factorial are the same thing. So a little rule here would be something like np n minus 1 would be equal to n factorial. All right. As it also turns out, npn is also equal to n factorial. And the pen. All right. So there's a couple of different ways in which you can get to n factorial. Now, if you want to do the computation, you'd never do it out this way. You know, math, probability, option 2 is the way to go. All right, let me get into the home screen. Math, probability, option 2. Wait, yours is different, right? Okay, well, mine's kind of awesome, but yours maybe is it awesome? I don't know. Really up to you. Math, probability, option 2. I put it in the wrong place. Okay. All right, you see how I call up the function and it just brings NPR into the home screen? You have to put the number, the n value in before the NPR, so 3, and then the r value afterwards. So I generally pretty much always forget to put the number in before selecting math probability option 2, so I end up having to make the adjustment after the fact, but in the end it doesn't really matter as long as you get it in the right notation or the right form. And so we get 3p2 is equal to 6, right? So it's not even worth going through it in this app because this one is so different that it's like, well, yeah, I'll just put the 3 there and put the 2 there, but that doesn't help you in your calculator. So anyway, restriction-wise, let me just talk a little bit more about this. We have 3 people that we're putting in basically 2-person arrangements or 2-person lines. So let me actually make the tree diagram for that. You know, a separate tree diagram, because I know I showed you what part of the other tree diagram was consistent with this, but I want to be able to manipulate this one because we're going to talk about combinations in a second. So any of the 3 people could be in position 1, and then position 2 is dependent on who's left over. There's only 2 people left over, so BC. AC, and AB. And so you have your 6 arrangements, all right? Now, and you can make a little note of that. 6 arrangements. Just scooch it. All right, now in terms of combinations, so I'm stealing my own thunder a little bit, but it's a good time to steal it. Combinations don't require the order to be represented in multiple ways. The ordering is reduced down so that we're only looking for unique pairings. So if I have AB as a grouping, then BA is just overkill. It's saying the same thing twice. All right, now arrangements and combinations, they have their own place in the hierarchy. So if you're running a race and you have, you know, the prize for winning first, second, or third place are all the same, then the only thing that would make it matter whether you came in first, second, or third place would be pride, right? That makes sense, right? Because the payout is going to be exactly the same. So if I'm just part of the top 3, I don't, that's fine. I win, right? But if the grand prize, so coming in first place, I get a flat screen TV. Second place, I get a $25 gift card for Target. And third place, I get a nice certificate with my name on it saying that I lost to 2 other people. So in those cases, it really does matter in which order you finish. All right. So the second case is the arrangement. That's the permutation. The first case is the combination. That's the case where I don't care about the order. All right. Depends on the context of the situation. Sometimes we care about the order. Sometimes we don't. Right. So in this case, it's not really given in much of a contextual situation. So I don't know. I don't know if I care about the order. But I will say that if instead of lining people up, I were creating groups for an activity, and if I read out the names and I said, okay, we got Alvin and Bart, you're group 1, Bart and Alvin, you're group 2, there's going to be a little bit of confusion. All right, so add a little context to it, and it shifts from being either a permutation to, or a combination to whatever it's not originally. All right, so what I would do here is I would take note of only the unique pairings. So out of this, I would highlight, you got A and B is unique, A and C is unique. B and A is not unique because I already have A and B. B and C is unique. CA, that's the same as AC, all right? And then CB is the same as BC, all right? I'm gonna put my pen back on. So we get 3 combinations. All right, so that, you know, in terms of like everyday language, that could be confusing because, you know, immediately you walk out of the classroom and you see an instance where something is called one thing but means another. So if you were to try to open one of those combination locks, you'd have to use a permutation to do it, right? Because it does matter what the order of the values are, right? If I tell you that the combo for a lock is 127.3, but you type in, if you turn it to 327.1, then you're not going to get in, right? So it's actually a permutation because the order is important, but they call it a combination lock, right? Maybe because they thought, they probably had focus groups, test groups back in like the 20s when they were invented, and they said, you know what, permutation locks sound stupid. I don't know. So we have 5 students in a class. Determine a number of 2-person groups that can be generated from the five available students. So we want 2-person groups. There's a couple of ways to do it. One would be to create a tree diagram. All right, so A, B, C, D, E. Now, these are still without replacement situations, although there are cases where with replacement could make sense. All right, because, you know, we're talking about people, so once I put them in a group, I'm not going to put them back in the, you know, put the names back in a hat to be selected again. You know, I don't want to have the same person assigned to a bunch of different groups. All right, but you got to be mindful of those cases also. But I can get from this that, all right, well, if A is the first person selected, then B, C, D, or E could be the second one selected. If B is the first one selected, then A, C, D, or E. A, B, D, or E. A, B, C, or E. A, B, C, or D. All right. So I kind of painted myself into a corner. I made my lines too close, so now it kind of looks a little messier. But it's basically in the second set. It's everything that I didn't account for in the first set. All right. So this would be the set of permutations. All right. So we're looking at, it looks like 20 arrangements. All right. Not what the question's asking us, but I got something I could work off of here. So what I want is the number of combinations. All right, instead of highlighting because it'll get a little messy, I'm just going to cross off the repeats. The repeats? Sounds weird. Repeats. So A, B I already have, so I don't need the BA. A, C I already have, so I don't need the CA. AD, so I don't need DA. AE, so I don't need EA. All right. BC, so I don't need CB. BD, so I don't need DB. BE, so I don't need EB. All right. CD, I have, so I don't need DC. CE, so I don't need EC. DE, so I don't need ED. All right, so just count up all the ones that I did not cross off, or count up the ones that I did cross off, so subtract them from 20, however you want to do it. 5, 8, looks like 9, 10.
4, 3, 2, 1.
4, 3, 2, 1. So it's a total of 10?
Yeah.
Okay. That's wonderful news. I thought there was 11 there for a second, and that would have been a problem. You know, it's not like, it's not the end of the world. It's just sometimes it becomes more of an eye test to figure out, okay, well, which one did I accidentally cross off or forget to cross off? You know, so the notation here is very similar to that of permutations, except we're going to use a C for combination. So I'm looking for 5 things taken 2 at a time. So individuals and the number per group. And that's something you pop in your calculator. Really the same way you do it for a permutation. All right, except it's math probability option 3. All right, so I could show you, but I'd be showing you the same thing I showed you in the last one. So type in the 5, math probability option 3, and then type in the 2. All right. So the question would be, okay, the calculator is going to tell us this, but what's the concept behind how the calculator knows to do this? And there's a formula, but really it's just in what way does a permutation become restricted in order to become a combination? All right. So the transition from permutation to combination . Now, the simple everyday way of saying it would be eliminate repetition. But that still doesn't give us the mathematical approach. Right? What we need to do is determine the number of different ways the repeated values can occur. Right? So determine number of different ways a pair could be repeated. And then you divide that into the permutation, all right? So, well, a pair, two things. We're looking for the number of ways two things could be arranged. Number of ways two things could be arranged would be 2 factorial, which is 2. So this would be the number of ways two things can be arranged. All right. So if you go back to what we wrote originally, we had the number of arrangements. We know that any pair of values can occur twice, based on the different orderings. So I just take my 20 and divide it by 2 and I get the 10. So you expand that out and you say, well, what if I wanted to have 3-person groups? You'd have to determine the number of ways 3 people can be arranged. All right, so that would be 3 factorial, which would be 6. I'd have to divide whatever this number of arrangements would be, 5p3, 5 times 4, so is that 120? And then I'd have to divide that by 6. All right, so you'd still get it, it's just it would be a different quotient that you'd be figuring out. And so what that does is it gives us our rule, which I put on the next page, I would imagine, I don't remember, I think I remember. But it's just basically this formula, but with an extra r factorial slapped on the bottom. Because r is the number of items per group, the 2, and that corresponds with the number of, whether it's pairs or trios or whatever, that need to be rearranged. All right? So, I've lost interest in that, I guess. So, if you go back to the tree diagram and really only focus on the cases that represented the combination. So we have AB, AC, DE, AD and AE and so on, right? Indirectly, and this is the beautiful thing about counting, is that sometimes a byproduct of what you're asked to compute is also something that's interesting or useful, all right? If I have 5 people in a room and I say, okay, I want to have, out of these 5 people, I want to have a group of 2, all right? So I got my group of 2. What did I just indirectly create? A group of 3 who are give them a name.
Remainder?
The remainders, the leftovers, the outcasts, all right? The forgotten ones, all right? Like you could go crazy with this idea, but it's you got what you needed, but indirectly you created something else, all right? So you created the hero, but at the same time you created the villain. It's a multiple origin story, right? So that's what's happening here. Every time I created a pair, I indirectly created a trio, all right? So I have group consisting of A and B. Naturally, I have the leftovers creating a group of 3, which is C, D, and E. And for each pair that I have, so each group of 2 I have a group of 3. Since I have 10 groups of 2, I naturally also will have 10 groups of 3. All right? So it's a natural byproduct, but it also creates a complementary relationship. So if I had something like, I don't know, I'll just make something up, 7C2, that's going to be the same as 7C what?
3.
5.
5.
7C2.
Right, because I've created groups of 2 out of the 7 available, which means I have 5 leftovers in each case.
Oh, okay.
All right.
Does that
So-
mean NC1 and then NCN minus 1 are going to be the same?
Exactly.
Okay.
And you could even expand that to say NCR is equal to NCN minus R.